So that's what we want to do, improve cycle efficiency. So now let's look at the initial example. So on the initial example, we have the TS diagram. Two, three, four, one. Now I'm going to put in here A and B. And I'm just putting that in because we're going to find those cycle state points. What I'm interested in is we're looking to find out what the average temperature of heat addition is. Because one of the things we can do is to raise the average temperature of heat addition, and I wanted you to see what that was. So when I look at a Carnot cycle, we have that the thermal efficiency is 1 minus Tc over Th. Well, this Th, if I can make this number bigger, then this becomes smaller and the efficiency goes up. So one of the ways we do this is to raise the average temperature of heat addition. So what I want to do is find out what's the average, how much heat is added here, how much is added here, how much is added there, and we'll see what that is. So Qn is equal to Q1A plus QAB plus QB2. And HA is equal to H sub F at that pressure, 1154.5. TA is equal to 264 degrees C. T1 is about 46 degrees C. So Q1A is equal to 1154.5 minus 196.86 is equal to 957.64, and TAV. So if I take the average of these temperatures, so if I assume it varies linearly, I take TAV as halfway there, it's equal to about 155 degrees C. So this amount of the total heat added is at an average temperature of 155. And now QAB is equal to H sub Fg is equal to 1640 kilojoules per kilogram at 264 degrees C. So we have this amount of heat. This amount of heat is at 264 degrees C. And then we have QB2 is equal to 3434 minus 2794 is equal to, these all have 0.4 minus, and this has a 0.6. So this is equal to 639.8. And this was at 500 degrees C. So at state 2 it was 500 degrees C. T2 was 500 degrees C. And we know that TB was 264. So TAV is equal to 382 degrees C. So now I'll look at the percentage of heat of each one. And so we have the Qn total was 37.54 kilojoules per kilogram. So now we'll look at the percentage of heat added at each temperature range. So Q1A is equal to 957.64 divided by 3237.54, which is equal to 0.296 at 155 degrees C. So nearly 30% of the heat is added at this temperature. We'll find out the percent at the other temperatures too. So QAB is 1640 over 3237.54. So this is 0.506. 50% is at 264 degrees C. And QB2 is equal to 639.8 over 3237.54 is equal to 0.198, nearly 20% at 382 degrees C. So we see that we can raise pressure here, and that will we raise the pressure, we can raise this part. We're going to talk about reheat, so how do we improve the TH? So when I did that 1 minus TC over TH, how do I raise that? Well, we're going to look at that, and one of the ways is to have reheat. So we're going to have reheat. So one of the ways is we're going to take the steam as it goes partway through the cycle, through the turbine, take it out and reheat it and add more heat to it. And another part is we're going to have regeneration, where we take some of the steam and preheat the water going into the steam generator. So we have reheat and regeneration. And we're going to look at these next. What we're going to look at first is a reheat cycle, where we take some of the steam as it expands through the turbine and reheat it. So I'll have a steam generator, a little more modest sized steam generator. And so we'll have that. Well, this is my feeble attempt at showing it being superheated. And then we go into the first turbine, T1, it's state 2. And then it expands partially through there, dropping in pressure. And then we'll take it and have it go back and be reheated and come back to the second turbine, T2, and expand through that to the condenser, to a pump, and back to the cycle. So we have 2, 3, 4, 5, 6, 1. And so we have that diagram, and we look at the TS diagram. Oops. Partially expand down to 3, back to 4. So we have 2, 3, 4, 5, 6, 1. If we look at example 15.3, we see that Qn, so look at example 15.3, go to the book, look at that. Qn is equal to H2 minus H1. So this heat plus the heat from 3 to 4 plus H4 minus H3. WT, so we have the steam expand from 2 to 3 and the steam expands from 4 to 5. WT is equal to H2 minus H3 plus H4 minus H5. And we have that WP is equal to H6 minus H1. And what the example does, so example 15.3, what it does is it takes a plant with and without reheat. And so without reheat, the thermal efficiency is equal to 41%. With reheat, the thermal efficiency is equal to 42.6%. So we see that there's a significant improvement in performance for the cycle when we add reheat. And so what we still have is the problem of this cold area. So this is fairly cold from a 500 degrees Celsius perspective. So what we want to do now is look at a regenerative cycle where we take part of the steam as it expands through the turbine and use it for preheating the water before it gets to the steam generator. And then obviously the next thing, because life is just too good thermodynamically, is we combine reheat with regeneration. Regenerative heating. And what we're going to use in this first one is we're going to use a direct contact heat exchanger. So we're going to use that. And that's where we have the two fluids mix. Direct steam water mixing.